In this video, we're going to continue our exploration of the mathematics of vectors. This time, though, we're going to do it with vector components. If you wish to go back and look at the tip-to-tail method, please see the previous video. Now, in physics, when we analyze problems involving vector quantities, we tend to not only draw the vector, but we also add a coordinate system. A coordinate system, like x and y axes, provides the basis for us to set directions for any problems. So here's an example with some vector I've drawn A, and I put in an x and y axis. You can see the positive x-axis is to the right, negative x-axis is to the left, positive y-axis up, negative y-axis is pointing down. Now, as before, you can draw the length of the vector to indicate its magnitude, and you can set a direction by using an angle measured from one of the axes of your coordinate system. In this example, I'm using the angle theta as measured counterclockwise from the positive x-axis. Now, you don't have to use this angle. As an example, I could show you that I could have set the direction by measuring an angle phi from the positive y-axis. But for this example, I'll keep it as I originally drew it. So, one way of reporting a vector is to write its magnitude, that includes a unit involved with it, and its direction, which you would write in terms of an angle that was measured relative to one of the axes of your coordinate system, like the x-axis or the y-axis. Reporting a vector in this way is called the standard form. I should quickly mention that in physics we sometimes use coordinate systems that are tilted, or there are other types of coordinate systems like spherical and cylindrical that we use quite often. So even if you have the same type of vector, here it's the same vector A, if my coordinate system is tilted, for instance, the direction would be given by a different angle. But it's still technically the same vector, the direction would just be from a different coordinate system. But there's another way to work with vectors, and a different format. This is called vector components. Now, I'm going to draw a vector starting at the tail of A that points along the positive x-axis, and then I'm going to add tip to tail a vector that points directly along the positive y-axis up to the point where it meets the tip of A. Because these two vectors combine to form A, we call them components of A, or parts of A. In this case, the components are perpendicular. We will call the vector that's part of A that points along the x-axis to be AX, and the part of the vector A that points along the y direction will be AY. Specifically, we call AX the x component of A, and we call AY the y component of A. Here's another example with a vector B. Now I'm going to draw the x and y components, but just for showing something different, I'll draw the y component first, and then I'll draw the x component. Now, you can do it the other way. The important thing is to make sure you get the right directions and to draw the x and y components correctly. Please use tip to tail. And I'll show you the other way where I draw the x first and then the y. Either way gives you the same result. Also, I'll show you that if we had tilted x and y axes, you could still draw the components, one along the x, one along the y. You can also notice in both these examples, by drawing x and y components, they are perpendicular, and as a result, they cause right triangles to be made with the original vector. This is the key to finding components, as we'll see next. In order to continue our discussion of this, we need to take a brief detour into the world of trigonometry, and we'll do a quick little review. Since with components we'll be dealing with right triangles, let's look at some of the trigonometry of that. Here's a right triangle with an angle theta I've defined. The long side of the triangle is called the hypotenuse, which I'll designate with a capital H. The side that's opposite to the angle is called, well, the opposite side, and I'll use a capital O for that. And last but not least, the side adjacent to the angle, which we call the adjacent side, which we'll use capital A. The first relationship we could look at comes from our old friend Pythagoras. That relationship is if you take the square of the opposite side plus the square of the adjacent side, it'll equal the square of the hypotenuse. The next relationships we'll look at involve the trigonometric functions. One relationship we look at is where we take the opposite side and divide it by the hypotenuse. This equals a relationship called sine of the angle. Similarly, cosine of the angle equals the adjacent divided by the hypotenuse. And the tangent of the angle is the opposite side divided by the adjacent side. In North America, many of us are taught to memorize these relationships by using the word SOHCAHTOA, and I'm doing that by outlining the letters in red. Just be careful, because you can define the angle in a different place on the right triangle, and that'll just affect what you label your opposite or adjacent sides. So always be aware of that. Now let's bring this knowledge of trigonometry back to vectors. So here we are back looking at our vector A and its components AX and AY. Now with this right triangle, we can define the magnitude of A as the long side, the hypotenuse. The magnitude of our X component will be the adjacent side, and the magnitude of AY will be our opposite side. I'm also using absolute value signs for these for the simple reason that with vectors, direction matters, and we'll see how to handle that coming up. And now I can write the trigonometric functions in terms of AX, AY, and the overall magnitude A. I can also write Pythagoras' theorem using these quantities as well. Okay, let's try an example. I'm just going to write here a force vector of A is 7.211 newtons. And it's also at an angle of 33.69 degrees as measured counterclockwise from the positive x-axis. Now step 1 to find the components of A is to sketch them out on the diagram. So sketch out the x and y components. So tip to tail, I'll first sketch out the x component, and then on the tip of the x component, I'll sketch out the y component. The next step is to use trigonometry to find the magnitudes of AX and AY. I'll use the sine of the angle theta to be the magnitude of AY over the magnitude of A. And using that, I can rearrange that equation and find the magnitude of AY. Plugging in the numbers, I get that the magnitude of AY will equal 4.000 newtons. Similarly, I can do the same thing using cosine theta to find the x component. And if you'd like, you could use tan theta to confirm your answers from doing it previously with sine and cos. Provides a nice check. But either way, we end up with the value for AX, the magnitude of it I should say, as 6.000 newtons. So there are our answers for AY and AX magnitudes. The thing is, though, we want to have directions taken into account because these are vectors. Step 3 is now to assign positive and negative signs to AX and AY so they indicate a direction. We do this based on how we set up our coordinate system. To do this, notice that on my diagram, the x component, AX, is pointing in the positive x direction, and so is AY. Because AX is positively directed, we refer to it as AX is plus 6.00 newtons. AY is also positively directed, so we say its AY is plus 4.000 newtons. Let's apply what we've learned to a different example, with vector B shown right here. Now I have a personal bias towards using angles measured with respect to the horizontal or x-axis, so I'm just going to alter the problem to have this angle shown, the 66.8 degrees. But as I said, that's my personal bias. You may like to use the 23.2 degrees that's already given with the problem. Now step 1, I'll sketch in my x and y vectors tip to tail. You can see the x points in the negative x direction and by points in the positive y direction. And I'm just going to rush through a little bit of the trigonometry here using the sine of 66.8 to determine the magnitude of by, and the magnitude of by will be 7.00 newtons. By the way, just as a little bit of an aside, if you were using the originally given 23.2 degrees as the angle, you would have to reverse what was considered your opposite and adjacent sides. So to find it, if you were to use 23.2 degrees, you'd have to use cosine of 23.2 degrees, as I've shown here. And I'll do a quick sketch of the x and y components if we were to use that angle. I'll just get rid of that and go back to finding bx using my 66.8 degree angle, and I find that the magnitude of bx will be 3.00 newtons. Now we have to go on to step 3 to find direction. Okay, let's go on to step 3. Now this time you'll notice that bx is pointing in the negative x direction, and by is pointing upwards in the positive y direction. So what we get overall for the x component of b is bx is equal to negative 3.00 newtons, and by is plus 7.00 newtons. Also, we can go the other way. If we are given the components of a vector, say we get ax and ay, and we wish to find its overall magnitude and an angle that describes its directions, we can go about doing that by just doing some of the reverse of the procedures we just did. So if we are given that AX is negative 2.00 newtons and AY is negative 4.00 newtons, and now we can figure out how to draw A and report it in its standard form with a magnitude and an angle measured from an axis. So I'm going to start by sketching AX out, and that'll go over negative 2 newtons, so 2 newtons in the negative x direction. And then on the tip of AX, I will sketch AY, which is 4 newtons, pointing down in the negative y direction. Then I can draw vector A starting from my starting point and pointing towards the tip of the last vector added. So there's my vector A. Now I have a right triangle, and I'm going to define an angle theta that I'm going to try and determine. Now I'm just going to resketch that right triangle using magnitudes so that the positive and negative signs don't cause me any confusions during calculations. Now that I know the magnitudes of the opposite and adjacent sides, I can use Pythagoras' theorem in order to calculate the overall magnitude of A. The overall answer turns out to be the square root of 20, or in decimal form, 4.47 newtons. Since I already know the opposite side and adjacent side, I might as well use the tangent relationship to find the angle. This will involve using the inverse tan function on your calculator. When I do that, I get an angle of 63.4 degrees. Now here's an important point. That angle means nothing unless you give it some context. For instance, that 63.4 degrees is below the negative x-axis. So I need to report it not only as the angle, but in relation to what axes of your coordinate system. There are other ways to report the direction. You could instead report it as 26.6 degrees to the left of the negative y-axis. You could also put the angle as 243.4 degrees measured counterclockwise from the positive x-axis. That brings us to the end of this video. In the next video, which you can click on right here on the screen, we will see how to use these vector components to add and subtract vectors. Thank you for watching, and have a great day.